here?
It's very,
No,
so I want him to hear about the problem.
you guys. really
So
appreciate
this
it.
one, when we will come in, we'll have to
Yeah.
minimize
But like,
Mhm.
Here's my comment.
the view on this.
It's good, right?
Yeah, no, that's fine.
Yesterday, oh yeah, never mind.
It doesn't work on TVs. They
That's
absorb,
good, because then I'll remember to do this, which is what I'm.
yeah, the screen absorbs the light.
There's some way to get.
Yes, to make it a
laser
laser. That's for the Zoom, so it has to be done in PowerPoint.
True, true. So let's go to Zoom. And it's up there. Laser color. Blue. And highlighter or. Highlighter, I want laser for it. And everybody will be happier.
Yeah,
Okay. Because we have some people on Zoom. Hello? Can you hear me okay?
see. There's nobody yet. It's just
When they speak to me, what speaker will I hear
Yes.
that?
from the TV.
From the TV. Okay, thank you, Nizit. So. I think
Okay,
we're supposed to start at 10 after or when?
Yeah.
Yeah,
10 after.
all right. Anybody tried the problem? You're gonna get a lot more out of the class if you try some problems. I'm gonna start with that. Problem I asked you to do last night. I'm gonna start with the solution of it. And then we'll go on to what the second lecture is supposed to be. Thanks for your patience yesterday. It was super long, but it allowed us to get to where we are supposed to be today. And
So is the next week also your lecture or art is coming
I don't
back?
know, I have to negotiate with them.
Negotiate.
has anything been decided about the midterm,
You mean the date? Or what?
date format?
Well, I think in the past, it's always been a take home that's a couple of hours long.
I see.
And it's usually after the normal midterm point, because there's no final, there's only a paper. So it's like 2/3 of the way through, so sometime after spring break. What else would be useful to tell you? It will include a little bit about the solids, but it'll be mostly on what Art's been teaching.
And what any specific expectations for the paper? What do you imagine the paper to look like?
The final.
Yeah,
Well, I don't remember if in the past Art mentioned any kind of a length limit, but I just remember seeing papers that were 6 to 8 pages, that kind of a length. It really can be a topic that you're interested in. You don't need to avoid topics that relate to your research. You don't have to do that. But it should relate to the class for sure. Don't come with a topic that nobody ever mentioned in class. That probably wouldn't be, but it's pretty free reign what you want to write about. Some direct connection to the class. Eric, we're talking about that the midterm is usually a little after halfway point because there's no final, that is usually take home in a couple of hours, but Art will explain all this because in the end, it's more his choice.
I thought there
It will have a little bit on solids.
I thought there was a paper at the end.
Yeah, there's a midterm and a paper.
I see.
Did I say something wrong? Did I garble it? So you'll have a take home or midterm, not too long. And it'll have a little bit from this section, but mostly it'll be from the pulse sequences. Maybe it will also, I think it will also include some of the relaxation material that's coming up. Okay. I think we're allowed to start. All right, so I asked you guys to think about a calculation so that the operational aspect of these rotations would be more comfortable to you. And I said, take the easy one. Just like simplified Hamiltonian. The important thing is I wanted you to compare Cartesian versus spherical harmonic. So the Cartesian. Anybody want to talk about how they set it up? We have a whiteboard, we have an answer key that you can turn around and look at. You can make any use of anything that you want. Cartesian will start with, let me check if somebody on Zoom said they wanted to explain it. No, nobody on Zoom wants to explain it. Hey, so the Cartesian is starting with an expression for the Hamiltonian. Well, we usually want a frequency, so I divide that by h bar, and to get a frequency, oh, it's cut me off. Just a little reminder at the bottom of what generally we might be doing to get a frequency. It's really cut off on the bottom.
If we change the view, maybe.
Change the view.
But that bar can be
In the
moved.
top right,
Top right.
it says view.
You want to show the whiteboard?
No,
No.
she just wants the bottom of the.
That's just like the bottom line of my slide is cut off.
There should be another version of Zoom where your PowerPoint is the entire screen. And you don't see the bar at the bottom.
Oh yeah, how do you hide that?
Yeah, I really want to get rid of it. Okay, can I go? Oh, I found it.
I think it's either view options or more. You can like hide the bar at the bottom. I don't remember how you do
This
this.
is making me dyslexic. No. It's giving me vertigo. Okay, spend all of our class time this way. Okay, let me go back to my screen and try more on my screen. Disable. Hide floating meeting controls. Does sound good, doesn't it? No, it didn't work. Okay, I'm just gonna read it to you. I want you to remember that, I naught in the top expression here, it represents, or Ix, Iy, Iz, it represents a measurement, but to get a frequency, it's a difference of measurement, and that difference is 1/2 minus 1. So we can, in the calculation of the frequency, basically drop that and move h bar over, and then we'll get the angular frequency in radians per second. So if you wanted to compare to an actual spectrum, you might have to, again, divide by 2 pi. But this is your calculation here. In Cartesian, this is your calculation. And you have an expression for the principal axis system, symmetrized, priceless version of the CSA Cartesian down here. And you have an expression for the rotation matrix here. So this is a little bit of cranking. But the fact is, I told you to pick an easy case. The easy case is that you're going to truncate it. So you only calculate the 3,3 element of the resultant. So this little sub 3,3. You're only going to calculate that. We are going to make it uniaxial. That means eta equals 0. And it's even better than that. The fact that it's uniaxial means that we don't need alpha or gamma because it's just one rotation. Now that might not have been clear to you, but it is true. So it allows me to get through this calculation. So I can get rid of eta, and get rid of everything except beta in this rotation. And then I'm left with something that looks like this. Is this the sort of thing, anybody who did this? Is this what your Cartesian looked like? The center here is the CSA tensor, except that I moved delta to the outside, so I just have numbers here. Okay, that's what the CSA tensor looks like if it's uniaxial and eta equals 0. The rotation, I'm using a shorthand, C for cos beta, S for sine beta. And I just need to multiply those three matrices. This is the easiest Cartesian you're ever going to get. It was still a little bit tedious. I mean, I had to do 2 multiplications, big deal. And then I took the 3, element, and then I had to do some algebra to rearrange it so that it looks like what we're used to. And at the end of all that, I did get this expression, which is a famous expression. It did turn out right. But I would not say it was quick. Did anybody else have a different experience with this, with the Cartesian calculation? Something you want to add to my discussion? Okay, single rotation, simplified Hamiltonian, and I would still use the word, and it's kind of tedious, like I probably would have preferred to be doing something else. Now, let's do the same problem, and yes, let's use the spherical harmonics that we learned yesterday. So it'll be truncated and uniaxial. The general expression for your Hamiltonian looks like this. Hamiltonian over h bars, because again, we're trying to calculate omega. You always have some scaling factor with your units, and then you do this double sum over the spherical tensor components of spin spatial. And those spherical tensor components have L equals 1. They have L equals 0. They have L equals 2. What do we need to calculate?
2.
Only 2. And we have to do the whole thing in the lab frame normally, but we don't know the spatial degrees of freedom in the lab frame. So that's why we need to figure out how to do a rotation. It's capital D. Now, if we only need L equals 2 components, but in particular, because it is truncated on the right here in the laboratory frame, we only do L equals 2, M equals 0. That's what it means to be truncated. We're only picking up the Z component. And because we're going to assume it's uniaxial just to make our job easy, in the principal axis system, the spatial degrees of freedom, we only want M equals 0 also. So in principle, L equals 0 has 5 components for each, and we could have up to 25 different calculations in the sense that each principal axis system, before we rotate it, could project onto all 5 into the lab frame. Okay, so starting from the principal axis system, it's purely M equals 0. It could only project into 5. But in a general case, you could have a lot more calculations than that. Does that make sense? So only terms we need from that table I gave you, we need to know what C is up here at the top. We need T20 and we need R20. And when it comes to the rotations, these expressions here that we went over yesterday, the only rotation we need to worry about is L equals 2, M equals 0, M prime equals 0. That's the only one. There's one term. Beautiful. And so we just need to know what this guy in the middle is called I, and I is this famous second Legendre polynomial. The whole process was not tedious. It was one of just conceptualizing, picking the terms, writing them down. So that's what we have here. We have T20. I picked that from my table. I have R20, and I have D200. I just went and looked for these things and I just wrote them down. That's all I did. Questions? Comments? And is the answer the same? Feels good when the answer is the same, right? But what about the process? Anything that it was mysterious because I was rushing? Like, something that didn't make sense?
I was trying to look at a problem in the handout.
Which problem?
The first one, which sets beta equal to pi by 2.
Oh, okay.
Beta is 90 degrees. So I was looking at that case, and this is a trivial point because we ultimately subtract out the isotropic component, but I wasn't able to get some elements of these matrices to match. But
Maybe because you had some things in the Cartesian that were actually not from L equals 2. Is that what you're saying?
Not quite. It was just that there is that 0, 0 element in both matrices, which is just the trace, right?
Mm-hmm.
And I think in one case it was 1/3 of that sum, so the isotropic chemical shift.
Yeah.
And in the other case, the 1/3 was missing. So,
Okay, so maybe let's just look at that. We can do it
yeah,
after class or during the problem session next week.
sure.
It could be a typo, or it could be that, you have to make sure you're starting with the traceless symmetric form of the Cartesian, maybe. I want to go up in complexity one step, and that is a really useful elaboration. We're measuring spectra, so we're still going to be truncated, but most CSA are not uniaxial, they're rhombic. So that's the next most complicated case. And the difference here is that for the spin degrees of freedom, I'm still in the lab frame. I still just want the 2, 0. But for the spatial degrees of freedom in the PAS, I need to keep not only R2, 0, but R2 plus and minus 2. Okay, so I'm just adding one term. Now I like this cartoon of the d orbitals and trying to think about what did I just add in. I still have the 0, 0 term, and I'm interested in only projecting it onto in the lab frame the 2, 0. Okay, so I have the 2, 0 in the PAS frame, which is delta basically, or delta delta. And in the lab frame, I need to project that only on the 2, 0 frame after the frame transformation. But now we add these extra terms. So in the PAS, we have 2, 2 and 2 minus 2. And they, in principle, can rotate to any of these on the right, but I'm only interested in when they project on to the 2, 0. Everybody good with that? So from this table, I still need C up here at the top. I should have put a red box around it. I need the T2, 0, I need the R2, 0, and the R2 plus or minus 2. Then it's a lot here. So let's do something to walk through it. So I'm going to do the sum. And I know that in the lab frame, for the spin degrees of freedom, I only want the 2, 0. So in the lab frame, for the spatial degrees of freedom, I also only want the 2, 0. Problem is I don't know how to write that. So what I need to do is think about the spatial degrees of freedom in the lab frame as having come from the PAS and been rotated to the lab frame. And we have a situation where we started from the 2, 0 in the PAS frame. And then we also have this situation where we started from the 2, 2 or the 2 minus 2. And I have combined them together to make this a little bit more compact, but really that should be 2 more terms, okay? Everybody good with that? The 2, 2 and the 2 minus 2. So what is that? So we already did this term, so we know the answer over here. The 2, 2 minus 2, we need to use a term that looks like this. And for the spin degrees of freedom, we knew what that looks like. That hasn't changed from the last probe. And actually just stay on that slide for one more second then. We need to fill in these rotations. This rotation for the m equals 0 in both frames, we also already looked at. It's just this that's new. And it has a slightly different presentation than rotation around y for L equals 2 and m equals plus or minus 2, but projecting onto 0. You have to go to that same table that we were on a second ago. Let me go back to it because I don't think I gave myself an extra copy of it. Here it is. And you need to pick these elements. You need C. And it's the same for both of them. So you need to pick this time. Root 3/8 sine squared beta. Is that all right? Okay. Back to our work. So that's what's been added here, but you see that there were other, just numerical factors and I've combined them all, so you'd have to do the work and double check that. The spin degrees of freedom, absolutely the same. So it's just, that additional term. So in the end, if you tidy it up a bit, it's the last line here for a frequency. You'd get rid of that spin operator and it's gamma B naught delta, and then the familiar second Legendre polynomial plus this extra term here. Not that much work. I mean, I found a way to talk a lot during it, but it was not actually that much work. Now, if you had to do that with the Cartesian, I don't think we would just be able to just do it in paper and pencil, right? And I think that it corresponds to many more manipulations, whether you're talking about a computer program or whether you're talking about pencil and paper work. We're gonna have more complexity in the next problem. So I think there's no question which we want to do. And sometimes it's nice to think about the physics in Cartesian space, but actually even that connection to the quantum mechanics is more natural in the spherical harmonics ultimately too. You can see things that change their quantum number or their total angular momentum by inspection instead of having to think so hard about it. So there are aspects of the physics that also become more clear. So sooner or later, everybody makes that leap out of the Cartesian and into spherical harmonics. But even with the spherical harmonics, some of the problems that we'll be interested in are very heavy in calculation. And so ultimately you do want to think about encoding simulations into a sophisticated program. And I'm just mentioning a couple of things here. Spinach, Ilya Kuprov, built in MATLAB. It's a significant investment to learn to use it. Simpson, which has less functionality, is much more user-friendly and just kind of transparent. Also, some that are intended as pedagogical for learning NMR, like Spin Dynamica, which is Mathematica notebooks from Malcolm Levin. So there's lots of this kind of stuff out there. So, you know, you're going to quickly reach the limit of what you really like to do in pencil and paper, but we haven't reached that limit quite yet, because I think it's not that tedious to look at how magic angle spinning works. And that's what we're going to do right now. It involves nested rotation frames, which we haven't done yet. And then once you have a frequency, actually thinking about how to make an FID and then a spectrum. These are two things we never spoke about yesterday. So this will be the new material. So the two frame transformations are that you might have a principal axis frame. And I'm going to skip some of the frames I talked about yesterday. We're going to assume there wasn't any motional averaging, so we don't need to do that. And I'm going to assume I don't need to make use of the crystal frame necessarily, because I'm not going to combine this with another interaction. So I'll just jump right from the principal axis system to the rotor frame. Because 3 frames is a lot. But we definitely need the transformation from the rotor to the lab, because that's the essence of magic angle spinning. That's where you get the rotor going. Okay, so what are the Euler angles for those two processes? The first process, as I said yesterday, we're going to treat it as a random number generator. It's just like we'll have one molecule for every orientation you can think of, because we crushed our sample and stuck it in the rotor, and so it's all this mixture, right? So we have to do many calculations, not just one, which is another principal reason why people can't simulate, even if you could do it at paper pencil, actually. For the second transformation, you have a time-dependent rotation around the z-axis of the rotor frame, omega RT, and then you have a polar transformation from the rotor axis up to the lab frame, and now you're in the lab frame. There is a gamma prime indicated here that would be to line up the y-axis in the lab frame, but we normally don't need to do this because there's no preference of x or y for most experiments. So there might be really only 5 Euler angles here. And if you think about it, these are both gamma from the first transformation and omega RT for the second transformation. They're actually both about the same axis. This is a Z rotation, and in between those 2 steps, we never moved Z yet. We moved it recently and we're going to move it again, but in between those, we don't move it. So you can just add those together. So in a way, it's really only 4 steps. So it's not as bad as you think. So we might be able to get rid of alpha if the interaction is uniaxial. That is not rhombic, not asymmetric. So in that case, we really only have 3 operations. This is getting very good. Now, I like these cartoons. I don't know if they are helpful to you or not, but it helps me keep track of what's really happening. We're going to start out in the principal axis system with only 1 spherical harmonic term. We don't need L equals 0 and 1 for reasons you guys already know. But we also only need 1 of the L equals 2 components because of an assumption we made. Perfect assumption for dipole coupling, imperfect for CSA, but it's very common in the literature. In the final lab, as lab frame, as per usual, we only need 1 spherical tensor component. I can't make any assumption about the intermediate frame. I have no reason to assume I could eliminate anything. There might be a reason in some problems, but I'm not smart enough to see it. So I'm going to have to crank through 5 options here, which have to mate 1-to-1 with 5 options here. So it's not 5 times 5, it's 5 pathways. That's it. Okay. And each pathway has 2 rotations, but we've boiled them down to just 3 actual operations. Make sense so far? I'm not going to do rhombing right now, so forget that I said that. Okay, so we're calculating this, the top line. It's our Hamiltonian and it's our frequency if we divide by h bar. It always has C out in front, which doesn't matter which term we're dealing with. It's just gamma for the CSA. And we match the tensor components between spin and spatial if we're in the laboratory frame. The problem is now that we need to consider that the spatial degrees of freedom represented by R are not in the laboratory frame in the way that we know them, so we have to rotate them twice. So this whole thing here, I finished with my coloring boxes. It should all be in one box together. This is an expression of the fact that we know spatial in the principal axis system, but we want to know it 2 frames later. So this whole sum here. And now we put the actual angles in the next line, just fill in from what we know. And fill in also the actual values for the spin spherical harmonic tensor components up here in the front, the last line. And since there's only 1 spatial degree of freedom in the PAS, I can actually fill that in and concretize it. So now I'm just left this sort of angle sandwich in the middle that I have to elaborate. What do I mean by that? But it's not going to be too bad. So is everybody good with the last line? Looks a lot like what we already did, except the angles in the middle are more complicated. Yeah, we did this already for the 1 transformation situation. Questions, comments? By the way, I don't think I pointed it out, but the superscript lambda, it refers to what interaction are we talking? And in every example so far, lambda is CSA. Could be something else, but. Okay, is everybody good with this? Ready to go to the next step? Specify the-
One second.
Yes,
Why the alpha was 0? Because the z-axis is same.
we set alpha to 0. And we set
Gamma prime.
one of the gammas to 0. Yeah, and that was again because of the truncation and the uniaxial. But the, let's say, inner angles, we have no right to set them to 0. It's the rotor and the turning of the rotor and the crystallite angle gamma that pairs with that rotor. We can't set that to 0. And of course, these two polar angles, they're never going to be 0, right? We just got rid of the first and the last. And they aren't 0, but they don't matter, so I filled in 0, and I'm not gonna.
The alpha would matter if I had a rhombic tensor, right?
Correct. Okay, so what are these things? We have to concretize them, and then we'll be home free. So let's take the first one. We don't actually need this. I don't know why I typed it up. E to the minus IML. This is what you just asked me about. I don't need it. I typed it up for some reason. Then I have the projection factor that corresponds to a Y rotation along beta. Then I have the two Z rotations about gamma and alpha prime, which is omega RT. And then one more projection for the magic angle. This last thing, I can skip it. So in the next line, I've skipped the things I can skip. I should have combined these two exponents in the middle. They can just be added. So it's really just this projection factor, gang these two together, this projection factor, which we're going to sum over m prime going from 2 to minus 2, although just like this. So m0 for the intermediate frame plus or minus 1 or plus or minus 2. But when we do that adding, I'm going to be joining the plus minus 1 terms and joining the plus minus 2 terms. So it's going to look like we only have 3 terms. I did this before. It's because they take the same form and they have the same factors, and it's just neater to write them together. Otherwise, these slides become so cluttered. So here's what we're doing, rewritten again, put all the constants and things with units out in front. And then we have this 3 angle sandwich, 2 Y rotations and 1 big X rotation in the middle. So first on the top line of these, I'm writing the 0, 0, 0 pathway all the way through, okay? And that one, because m equals 0, you can get rid of these phase factors. So it's really just the 2 Ds. It turns out to be an important term. So we have to look up this D, L equals 2, m equals 0, m prime equals 0, unless one of you guys remembers it. Yes. So we're going to have 2 second Legendre polynomials right here. Okay. In the next line, we have something we never used it before. We have the L equals 2, m equals 0, m prime equals 1 type terms. So we have to go back to our table of angles to find out what that looks like. Then we have this phase factor, and then we have another one of those. So because the path's starting in with 0, it's also always going to be 2 matched terms that get multiplied. And we have one of these for the intermediate m is 1, and then one for the intermediate m is minus 1, and they're going to look very similar. Finally, we do the same thing for the intermediate m being 2 or minus 2. So I did it. I worked through this for you, and I looked up what those things are from the 5x5 table. But does everybody who's listening along feel pretty confident you could do that for yourself? Go back to that table. You can figure out which term you need to pull and fill it out. You good? Is that all right with you? Or should I go get it? No, let's just go get it. If I'm not getting answers, I'll go get it. So I have to go back to this table. Should I put another copy right there? This is so far back. So now, for the first time, I'm needing terms like this, like one of them is 0, but the other one is 1 or -1. And you notice these are all the entries here are G, but they might be positive or negative, and G looks like this. √3/8 sine 2 beta. We didn't have to use that before, now we have to use it. We had a need before for this where one of them is 0 and the other is 2. That is going to be a C. And we used this before, √3/8 sine squared beta. So you're going to see sine 2 beta and sine squared beta turning up in those two terms respectively. So for the m = 1, it's sine 2 beta. So let's go back to our work. Yeah, so here we're supposed to see sine 2 beta and some factors that you'll just have to trust me or not. And then for the plus and minus 2 terms, we got some sine squared beta terms. That's where they're coming from, okay? Those are just your rotations along these different paths. And then I just cleaned up the math a little bit. This last step, can anybody tell me what happened here? Those were phase factors and now they're cosines or sines. That's a famous substitution, okay? That we use all the time, flipping between sines and cosines and imaginary exponents. So that's what we have. It's kind of a lot, but can you imagine if we had to do that with the Cartesian? There would be no vision, like you wouldn't be able to understand what any of these terms are actually coming from. Another advantage whenever you have that kind of organizational concept in simplifying your math is that the other thing that's much, much easier is proofreading. You can separate the pieces and go back and look at them one day later and make sure you didn't, So there's just no comparison. Now, I want to talk about the features of this solution. So that was an expression for a frequency. This is a frequency. And what is meant is that that is out in front. This is not a column vector. This is just 3 terms we have to add up, okay? I just typed it that way because it's awkward on the page otherwise, but this is not intended to mean a column vector. So what are the properties of these 3 terms? The first thing that I can see is that the top one is constant, doesn't have a time dependence. It's geometric, but it's constant. It has a piece of geometry about which crystal I picked, and it has a piece of geometry about the rotor and where you put it. The second 2 terms are time dependent, and that's beautiful. They're just like harmonic, perfectly harmonic. They're going to exactly average to what over time?
0.
0. That's really cool. Now, you might have thought because you were rotating your sample at omega r that the frequency would vary with omega r, right? But look what happened. You got an omega r piece that did happen, but you also have something which is time varying with double omega r. Of course, each one also has a phase factor, and that's just a kind of a goofy thing about the crystal light selection. And we'll look at that more later to try to get some physical intuition about what that means. But it's important to recognize that because we work with second rank tensors in almost everything in NMR, that when you have a systematic motion in spatial coordinates, you don't just have that frequency component in the modulation of the Hamiltonian, you always also get the double. It shows up in lots of experiments where you say, why don't we have another sideband? Or what, and this is usually the answer. This is a second rank tensor. So the other thing here is the magic. Okay, look at the first term. This first term is actually horrible because it's a power pattern. You see beta, you're going to pick so many different betas, right? And you pick a different beta, that's pick a different crystal, like place it differently, going to get a different frequency, and the span of those different frequencies is not small. This thing out in front, it's gonna go from that to minus a half of that. That's like 20 kilohertz for some systems. That's horrible. That's a horrible term. That's the term we are trying to get rid of. And our game plan to get rid of it is what? How are we gonna get rid of that term?
Make the other one 0.
Thank you. This one right here is being multiplied by something that I get to control. So if I set that perfectly, and perfectly means that I make the term go to 0, which in turn means that the angle has to be the arc cos, the square root of 1/3. It's kind of a funny deal, but that's what it is. It's a 0 of the second Legendre polynomial. Then that whole term goes to 0, and I won't have a little powder pattern on every single one of my lines. If I'm misset, I'll keep a little piece of that. So that'll be a strictly inhomogeneous contribution to the line width that won't have a Gaussian shape. You can do it one day. You can be on the instrument and just deliberately take a spectrum at the wrong angle and see what it looks like. That's interesting. But don't do it on our new cryoprobe, because that's really common. There are old experiments where it's done deliberately. I don't think that it's the most elegant way to do this, but like, let's say you could hop the angle. You have to do that for some of the automatic eject insert anyway. So you're taking some of your spectra with the angle properly located. And then in an indirect dimension, you come up here and do something and then refocus all your magnetization back. And then you come back to measure down here again, something like that. So you could measure a powder pattern instead of using pulse sequences like what you normally do. You could use a mechanical approach to measure your powder pattern. So overall, if you got the angle set correctly, the time average of the entire thing is 0. So where's your peak then? If the L equals 2 is all zeroed out, where's your peak?
Isotropic chemicals.
Right, because we always had that L equals 0 term. It didn't go away. We're just not including it in our calculation. It's our reference point for all of this. So it's solution-like. Pretty cool. I already said that. It's interesting to think about individual crystallites sometimes, because that's a thing you can do with pencil and paper, and some of them are funny. So you could have a crystal orientation where beta is 0, meaning that the PAS lays right on the rotor axis. And it'll stay that way for the whole experiment, right? Crystallites are not moving within the rotor. And that one, turns out, has no time dependence. So it's always isotropic shift. Or, other things. You can look for other special crystallites. There's some that have the biggest swing in frequency, some that have the least swing in frequency. It's sort of interesting. So here's a summary. We did this calculation on the top, or I could have gone all the way back to the original form. And we got this answer that not omega, but it's more proper for me to say omega of time minus omega iso. And I'm really giving a complete picture. Will be equal to some constant times a function that varies according to cosine of omega RT, and some other constant cosine 2 omega t, and we do know those constants from the work we did. It's pretty elegant, pretty simple little frequency expression. Now I have a couple of cartoons here for you to enjoy before we take the next step. The magic angle, you might know this already, is the cube diagonal. That's comes up in other experiments, and it's of course the same angle for dipole interactions. There's nothing different about that. And the second rank tensors, and they're strictly uniaxial, so everything would apply. So when you spin at that angle, you not only average your chemical shielding, but you average the dipole coupling to 0. I'm just including these spherical tensor operators for dipole couplings for convenience. We don't have a problem with them in front of us right now, but just, you see the analogy now, you can do the same thing. We'll use them if I get to another lecture. Okay, and I like this sort of old school thing, forget about the cartoon on the left for the moment, that we think about as the rotor advances, that the frequency is something you could plot, and it would have two Fourier components. It won't always start at 0 or max or min, or it starts someplace arbitrary, depends on your crystallite and all of the Euler angles describing it, but it's just a kind of a graph tells a story better than an equation for some people, so. Now, sum up. If the angle is set correctly and the rotation is fast enough, everybody averages to 0 and you get a solution like spectrum. If you spin more slowly, there are two things to understand about it. One is that there will be a point at the end of every rotor cycle where there's no effect of those sinusoidal functions, right? You'll be back to wherever you started. It's the property of a sinusoid, and also its first harmonic, double frequency. So one thing you can do if you happen to want to spin slowly is just detect stroboscopically every single rotor cycle. That's when you take your data point. Your 12 must match your tau r, and you're going to get a normal looking isotropic frequency. Anybody think of a reason why you might not want to always do that? Rotor synchronize your 12 or your data points.
The spikes.
You could get some kind of artifacts. I don't know with modern instrumentation if that's that much of a deal now anymore, but
Constraints on spectral width.
that's what I was thinking of. If the premise was that you were spinning slowly, now you're going to have a really small spectral window. So it will only be good for some kinds of systems where it's not a big deal. But it's good conceptually to be aware of this, that for indirect dimensions, for example, you could just hit, then you won't see spinning sidebands, and you'll get more signal because all of the signal will contribute to the center beam. So sometimes it's a useful trick. If not, then obviously with this time dependence, you're going to get something more complicated than just a center band. So how does that work? Before I answer that question, like what does this frequency thing do to your spectrum? I just want to show you the resultant of putting the rhombicity back in, because for CSA, we really shouldn't be dropping it routinely. And so you add some more terms. So the general expression is still the same, nothing different in the block at the top. But we are going to add more terms because we cannot assume that alpha is 0. We cannot assume, you know, the first angle relating PAS to rotor frame. We can't assume that that's 0. We can't assume that the PAS L equals 2, M equals 2 is 0. So a bunch of new terms pop back in. Here's what the resultant is. We already saw this term C1 that goes as omega RT, and this term that goes as 2 omega RT. But they're slightly modified. C1 and C2. And now we have these sinus terms with their prefactors. That's a more complicated derivation. It's just more terms, nothing conceptually harder. But there's a more opportunity for human error. If you didn't want to just repeat what I did and check it, if you didn't feel up to that, what else could you do to check if you believe this? see what happens if you set alpha and eta to 0 and see if it defaults to the other equation. Because most people who have an error in something like this, probably a sign error or a factor of 2 or whatever. So you can just, you can look to see that the limit of this as eta gets really small and alpha is almost 0, gives you the right. But you might need this form of it because you might not want to assume that eta is 0. Okay, so here comes the new conceptual piece. How are we for time? Okay. Because this today should end at 2:30, is that right? Yeah. We have a frequency. Normally, when we simulate spectra, we just have the frequency for all time, and then we can go get another frequency for another peak. But this is different. We have a frequency as a function of time. That's weird. So there's different ways you could handle that. I am going to approach it in the following way. The frequency is a function of time. I want to follow one crystallite in the XY plane. By integrating the frequency, I'll get its accumulated phase, instantaneous accumulated phase. So that's like saying I know what mx and my are as a function of time. Just integrate that equation, whatever the equation is, you integrate. So then you get phi of t, which is sufficient for saying mx, my, what are they? But I'm not going to do that. I'm not going to Cartesianize it. I'm just going to have this delta phi relative to wherever it started, if it started on X or Y or whatever. What is the change, the evolution due to its frequency? Accumulated phase. And then the way I like to think about it, what you do with that phase is you exponentiate it, because that's what an FID is. It's the exponent of the phase. Everybody good with that? So that's writing as a mathematical function with complex notation, kind of like making m plus I, mx plus I my, something like that, right? Just exponentiate the phase. Cosine delta phi plus I sine delta phi, but we're going to use exponent notation. Now, if that's a correct mathematical expression for our FID, all we need to do is Fourier transform, and we should be able to see our signal. A kind of closed form expression. I know. That's what we wanted. So putting that all together in one equation, the signal as a function of omega is e to the I delta phi t times e to the minus I w omega of t. That's the Fourier transform bit. And then you integrate that over all time, and you get a function of omega, this spectrum that you wanted. You're going to have to do that for each crystallite. What do you suppose would happen if I thought, I'm so sick of these powder averages? They make everything literally 500 times slower. I want to just average the properties over the crystallites and then get my FID. What do you think would happen? Average over all the crystallites to get things like angles and, predicted frequencies and whatnot. So I don't want to have to do an FID for each crystallite. I want to pre-average them and then do this math.
Would you lose the variance?
Totally. You've turned it into a solution thing before you even started. Yes, thank you. So we got to do all the crystallites, but we're not really doing that in the lecture notes, but just a reminder. So first step of that was to turn a frequency as a function of time to an accumulated phase. So delta phase is simply the integral of that frequency expression that we have from 0 time, using a dummy variable for time, up to the actual time you're interested in. And the total accumulated phase for the isotropic shift is simply iso times t. So possibly the easiest thing is just to take that out and just accumulate up the anisotropic part and pretend that your rotating frame sits at the isotropic shift. Now, our expression for The anisotropic piece, the L equals 2 piece, is this stuff. So if we integrate it, it's not that hard. So when you integrate a sinusoid, of course, you end up with the frequency as a quotient with the original constant. So all of these terms are like some geometric thingamajob, like C1 is some angle thing, but divided by the frequency. All of the prefactors are divided either by omega or 2 omega. And that's interesting. So the accumulated phase, talking about you have some magnetization moving in the XY plane. The accumulated phase is how far we'll ever get before what happens at the end of the rotor cycle. It always comes back. We mentioned that already, right? So as I turn the rotor up, he never gets quite as far. Now double the frequency again. This is this picture that he'll stay kind of close to the isotropic shift if omega is fast enough. His accumulated phase is limited by this 1 over omega dependence, which just formally came out of integrating. Does that make sense? So as omega becomes large compared to what? To the absolute value of C, which is like delta over 2 or something like that. So it's related to delta. So when omega is much bigger than delta, you kind of like don't leave the place you're supposed to be with just the isotropic shift. Your ditherings become smaller and smaller. All right, so the thing about this expression is it's, it has limits. So you have to remember to evaluate it at t, but also at 0. So when you do all of that, delta phi is this expression. So evaluating at t and evaluating at 0. That's how we grew up to 8 terms. And if you want it to look simpler, you can just get rid of the ones in orange because that's only if you include the anisotropy. So there's this dependence on gamma that seemed kind of weird, like how is my frequency really dependent on gamma? But it partly goes away once you think about the accumulated phase and the integration limits. Oh, so I didn't have to wave my hand around. I had a picture for you. I forgot. I had a picture. So delta phi is something like, little delta, the CSA anisotropy over omega. And so it's moving, and I show it as kind of being subject to T2 and getting smaller and smaller just so that I can make a clearer picture. But it goes to an extent that depends on that ratio, delta over omega. And when it's fast enough, you stay right at sigma iso. Looks like a solution spectrum. Okay. So this is your FID. Which can also be rewritten in this way. So you started at some reference phase, X or Y, that's what this phi 0 is for. And then you had this accumulated phase that we just calculated. And that's a function of time. So that's would be normal if delta phi was a simple function, but delta phi is itself a trigonometric function. So what we're dealing with here is an exponent of a trigonometric function. It's a slightly unusual thing to have to deal with. And then Fourier transform. I don't know, does it look like any physical problem you've had to think about before? It's like a cosine of a cosine. It's in the same family of functions, or an exponent, a complex exponent of a complex exponent. Did you ever see this in any physics or engineering or math class before? maybe just to give you a tricky derivative to do when you were first studying calculus, maybe that's the only place you saw it. I wasn't that familiar with them before I studied solid state NMR. I think it's unusual, but it does show up in engineering problems. I mean, if you think about it, amplitude modulation of signals, like as in AM radio, is sort of a normal-ish kind of mathematical function, but frequency modulated is sort of like this. But we get to think about frequency modulation that is following certain symmetries and natural cycle, purely repetitive mode. So it's a relatively simple example of frequency modulation, a relatively elegant example. So yeah, so I need to do this exponent of a trigonometric function, and then I need to Fourier transform. When you see something weird, sometimes you're thinking, can I try an expansion? Like, what can I do with this? That might be helpful. But it turns out that there is a basis set function and a famous problem with famous solution that does correspond exactly to this. So the frequencies that you will detect after Fourier transformation will be harmonics of the argument of the sinusoid. And this can be recognized in problems where you use Bessel's functions. They're typical for problems in cylindrical coordinates that have a kind of frequency modulated type behavior to them. So the Bessel function, J of X, it comes up when you're trying to look at the exponent of a sinusoid and you want to express it in some series. So you might have wanted a Taylor series. This is just a different series. This is a different approach to it. And it may have a correlate if you had tried the Taylor's expansion. But anyway, this is the expansion. So you say, here's a good basis set for expanding this. What I'm going to do is I'm going to say, I've got these other functions that are normal, e to the I m alpha, not e to the I something or other sine alpha. I just want a normal function. So I'm going to have e to the I m alpha. And that doesn't really look that much like this function. But then I'll sum over a whole bunch of values for m. So it's like a harmonics that would approximate the behavior of this exponentiated sign. Well, what are the coefficients to recreate this function? That's what a Bessel's function is. It's the coefficient to recreate this funny function with a normal collection of exponent type functions. All right, so what's the value of J? Well, J has this crazy expression. And what's in here? Well, it's itself is an expansion or a series with a parameter P. The Bessel's functions, of course, you have a collection of them because they are coefficients for a series whose index was m. So J is going to depend on m, but it itself is also a sum, so now it depends on P as well. Now X is important here. J of X, what was X? X was the thing in front of the sine function in your original function. So what is X for us? It's like C over omega. Okay, so you're saying, okay, I've got an exponent, and it's an exponent of a sine function, but how big is the amplitude of that sine function? So is it just a little bit frequency modulated or a lot? That's X. X is, you see a lot of parameters here. X is kind of in a way the most important of them. So if I would go to large X, these values tend towards 0. Going to large, Yeah. If I go to large X, they default to 0. And also if I go to X equals 0, they default to either 1 or 0. And in between, they're a bit crazy. So if I use these Bessel's functions, I can rewrite or create an expression for our Fourier transform sig, which we'll look at in just a second. These are just different plots of J for different M values. And again, as X goes to 0, they have a good limiting value. And as X gets super large, they slowly tend towards it. Okay, so our terms look like this. Instead of I X sine alpha, they are I, and then this parameter I was talking about before. How big is delta compared to how big is your spinning frequency? And that's like saying, how much frequency modulation am I really going to have? And then the sine is to do with your rotor frequency. Okay, so this is our function. And I can express that as a normal function, e to the I omega R, with a phase factor and harmonics. And each one of these terms for different M values, how big is it? I need to go look up my Bessel function. So simulating spinning sideband patterns for solid state NMR, some of the initial programs did exactly that, like the Hertzberg programs, algorithms, make use of these Bessel functions to estimate the frequency components in the signals. So this complicated function is here, in effect, being expressed as a center band where M equals 0, a first sideband where M is 1 or minus 1, and so on and so forth. Now, a funny thing about this is that we have no reason to think that M is limited in our data. Like that we would stop at a certain value of M, and then that would be our last spinning sideband. I don't know, if you saw static spectra, and then you saw MAS spectra, you might have had the feeling I had originally that my isotropic shift, my static spectrum, what I was thinking incorrectly, I only have one color. So sad. Anyway, it doesn't matter. I was thinking you would get, spinning sidebands that would sample like right through here. Oh wait, I have to be at the isotropic shift.
Save a red one.
Oh, thank you. So there's my static spectrum in black, and then I was thinking my MAS lines would be like that, but how could I have a frequency that I didn't have on my static spectrum? No, I'm not thinking with any physics. I'm just kind of like guessing, right? There shouldn't be anything here, right? But that's not true. With this expansion, there's no formal rule that says M has to be limited to the original spectrum. Also, because it's a second rank tensor, you're probably always going to have a couple of extras on the outside. This business of being modulated by 2 omega will contribute to having more substantial spinning sidebands outside of the powder envelope. But if you look at actual spectra, it's true. You get, they're not artifacts, you get actual frequency components when M is higher than what would have been inside the envelope of your spectrum. So we can look at some limits here. What if we had very fast spinning and low anisotropy? So omega R is much greater than delta. In that case, these would tend towards 0, right? And so you can see these functions, J0 tends towards 1, when X goes to 0. And all the rest of them tend towards 0. So that's intuitive. As you jack up the spinning frequency, you will end up with just a center band and no sideband. So the limits of this are behaving pretty well. And that will be true for every single crystallite. See, did I have another limit or did I just stop there? Then you can formally write out an expression for the FID, including this expansion. And I don't know that we'll really be making much use of that in this class, but just to expose you to this kind of thinking. And from that, you can get an amplitude for the K spinning sideband. Now, what we will be doing more of is writing Hamiltonians as time-dependent objects and applying that to predictions of outcomes of experiments with like average Hamiltonian theory. Sometimes trying to remove some effects by maybe like a frame transformation or something. So we're going to work a lot with the time-dependent Hamiltonian and less so with this FID, but this just kind of gives you an exposure to how people think about it and why the spinning sidebands are there. So the third part of this, we have time to start a little bit. We won't get that far into it, but maybe just to expose you to it, and then we'll see if at another time, part of next week or later in the term, if we can finish it. So do you guys want to just think if you have any questions or any comments before I start totally different topic? Yes, please.
So does this mean that both the CSA and the dipolar interaction result in spinning sidebands?
Yes, it does. You have dipolar spinning sidebands. So why aren't we talking about them all the time?
Yeah, the decoupling, is that why we don't talk?
Yeah, and then homonuclear dipolar sidebands. Carbon, we're almost always spinning much faster than the
Yeah.
carbon-carbon couplings. And then many studies are done without direct neighbor dipole couplings. And then protons, there is a contribution. And if you look at like a dense organic solid with lots of protons and you look at fast spinning, there are some spinning sidebands. The contribution is not purely CSA. Now, there are ways to separate them besides decoupling. There are other things that maybe are related to the next topic up. How can you manipulate CSA different than dipolar? So there would be ways to get one and not the other beyond just decoupling. But normally, if you just had strong couplings and a weak CSA, it's a mixed contribution.
So I mean, this also applies to, I guess, the spin one quadrupole where the interaction is say 5 times stronger than my spinning speed. Then I in principle have spinning sidebands.
Deuterium. Yeah.
So I do have.
Not in principle, in practice. We had lots and lots of those spinning sidebands and we used to analyze them. To do what? To get motion like order parameters to see if there's a paramagnetic center near it, then you would have the sum of that paramagnetism plus the quadrupole. But yeah, you get these quadrupolar spinning sidebands. Yeah.
But you can't collapse the line shape onto the isotropic chemical shift, right? Like, for example, in proton homonuclear, when I have homonuclear dipolar coupling, like 20 kilohertz protonated solids, I have broad line shapes instead of lots of sidebands. That's what I'm confused about. Does that make sense?
Let me see if I'm hearing you right. The effect of neighboring spins might contribute to spinning sidebands. In like a really simple Hamiltonian, that's what you would think. We do the theory with, but you know that in practice, actually, it seems to affect the line width of the center band more so, and people are talking about that more. Is that what you mean?
Yeah, like 20 kilohertz,
question.
100 kilohertz, I see a narrowing of the proton signal in protonated solids.
Yes.
So,
Yeah. So the center band, is gonna be a width, will be affected by things that are like relaxation type processes or chemical exchange type processes. And anything inhomogeneous, meaning like I'm calling this peak all the same methyl group, but apparently, you know, this one is shifted a little up and that one's is shifted a little down. And that includes misset of the angle. Okay? So the center band could have inhomogeneous contributions, or it could have relaxation exchange type contributions. And the dipole couplings certainly contribute to that. And we talk about that more. And it's a particular problem when you have a whole network of coupled spins. It isn't just one neighbor. So it isn't a clean Hamiltonian. And it's like you can have a big enough system that in some sense, like quasi-irreversible things seem to be happening, spin diffusion, and you don't know how to recover it, and so on and so forth. So there's a no man's land between those two pictures. Let's say I have literally two spins, a CH system, like nothing is talking to them. They're on their own planet. You could get beautiful sidebands, and there's not necessarily any reason to think that it would lead to relaxation. It just depends. Maybe it would, but you need motion and some other things. And now in the spin bath picture where every proton has a million neighbors, it's mostly relaxation. And there's a kind of messy place in between that has attracted a lot of really, really smart theorists to try to work on it, but you end up with like end effects and things like that. So you know, you have maybe 10 spins and funny things happen on the edges and whatever. And when Mikhail Verstort made this amazing program, Spin Evolution, that was part of the science he was doing on it, is like large but finite spin networks. And can you kind of understand what's happening with these couplings when it's not a spin pair, but you're not just gonna
Yeah.
throw your hands up and say it's bad, whatever that is. Other things, anybody? Yes, please.
I have kind of like an open question.
Good.
So for the last slide, that was comparing like the liquid versus the solid state. I have a question about the in-between. So part of what I'd like to do is work with cell-like conditions. So having that in-between of like this jelly-like cell bag, how could magic angle spinning contribute, and would you see the sidebands?
That's a great question. So in between these two limits are many, many important systems. It's not a perfect liquid and it's not a static solid. And we have here at NYSBC something called an HRMAS probe. It's just a probe that does magic angle spinning, not that well, but it shims beautifully like a solution type probe. And popular for studies kind of like what you're talking about. So high resolution MAS. What's the MAS doing for you? Probably removing shimming problems more than anything, like the material that you have as mesoscale inhomogeneities and its magnetic susceptibility, and by spinning, you don't have to worry about it. You might get spinning sidebands from that too. Like you could get spinning sidebands from all sorts of things, right? But will you be able to use the pulse sequences I was about to introduce? If the motions, if the correlation time of the system is, let's say, microsecond or shorter, probably not. Probably these pulse sequences I'm about to talk about aren't going to work very well. Will you be able to use J-based solution-like pulse sequences? Maybe. And that's what people do in those probes mostly. But your need for things like deuteration might be intensely more so than normal solution NMR samples. Yeah. We can talk more about that in Maybe you want to, try writing your paper about. All right, so when we have magic angle spinning and pulse sequences, a lot of times we just say, well, the FID is how it normally is. That's not the focus of what we're talking about here. The focus of what we're talking about is how can we move magnetization from spin A to spin B? And how can we not have famous artifacts from other terms in the Hamiltonian? So we want to list all the terms in the Hamiltonian and think about how each one will behave under spinning and then spinning with pulses. So under spinning, so far it seems kind of simple. It's like everybody gets hosed. That's it. That's the whole story. But then spinning plus pulses is a super rich story. So magnetization transfer, as you know, is essential for multidimensional experiments, enables distance dynamics. We like to think about the non-existent hypothetical isolated spin pair, and that's what we'll be talking about today. And we're going to be shifting from our focus on the chemical shielding to the focus on the dipole coupling and those operators table that I gave you before. I like to remember a handy number, and this is cycles per second, not radians per second, but it's about, not exactly, but about 120 kilohertz for 2 protons at 1 angstrom. And then you can scale by your gyromagnetic ratio and your cube of your distance to think about the different strengths of the different dipole couplings you might be encountering. It does take the anisotropic form, so literally, of a uniaxial second-rank tensor, just like we've been working. But instead of putting delta out in front, you're going to be putting the dipole coupling, which generates shifts, but more interestingly, it generates like spectral shifts, like sidebands and things like that. But more interesting, what we're going to talk about if we continue this next week, that opportunity to move magnetization. So there may be things called flip-flop type processes. That means I have 2 spins. One guy maybe goes up while the other guy goes down. So it conserves angular momentum. Maybe not energy, depending on if they're homo or heteronuclear. But we will also see, and those might also be called zero quantum magnetization transfer situation. But you might also see double quantum processes where the dipole coupling's effect on the system is to flip both up or flip both down. So the first example is going to be the Hartmann-Hahn cross-polarization. And it's used in solution NMR as well, but it's a kind of a go-to move for solid state NMR. Although Larmor frequencies are not matched, or unlike spins, right? So nitrogen and proton, you never mistake one for another in your spectrum. They're very, very different frequencies. It is possible to make their Rabi frequencies match. So instead of gamma B naught, a Rabi frequency is gamma B1. It's the nutation frequency, the great circles during RF that we're talking about here. And it was a work of Sven Hartmann and Erwin Hahn, following some training by Isidore Rabi, to think about matching Rabi frequencies instead of Larmor frequencies. And then you can transfer magnetization from anything to anything, from an electron to a carbon. You can just do it. Now, I'm going to end here because the time's up, but I do want to tell you, Sven Hartmann was in our physics department for many years, past time before COVID. And he was a student of Erwin Hahn, who was a professor at Berkeley. I.I. Rabi was also a physics professor here at Columbia, and was his experiments can be counted as some of the very first observations of magnetic resonance in a kind of a general sense. And he had great contributions to wartime efforts, basic physics, and we have a scholars program named after him at Columbia. And these are some funny pictures of them. So Their work leads to the first example that we would look at if we get another lecture period together. So how do you move magnetization with the dipole coupling and matching these Rabi frequencies? And what's a good average Hamiltonian treatment for that? And it is an exemplar for looking at lots and lots of other pulse sequences. You see how you do this one, then you can kind of get a glimpse as to how to do lots of other pulse sequences. So that's it for today, I think.